a little bit about Rouche's theorem, which I've got up here right here. And then maybe show a couple applications of Rouche's theorem, and then maybe give you some pointers on how to use that, and then we'll talk about the exam on
I'm
Wednesday.
going to push it back to Friday.
Wednesday?
Wednesday, Thursday?
You said Friday, right?
No.
No, but you said that you have culture night.
Yes.
What? No worries, yo. Just push it to Friday.
Yeah, it's okay about that.
Just push it Friday
Stop
morning.
it, I didn't.
You want to? I'd rather do it on Friday morning, actually.
No.
Yeah, because there is a holiday right after Sunday.
Oh, Monday's a holiday?
Yeah, next Monday
Oh,
is
yeah.
a holiday. So we can just take the test on Tuesday.
Okay.
Well, I was thinking Friday anyway.
It's not like it's going to be on Friday then.
No. Oh.
Yeah, Friday to a Monday. Oh,
Okay,
wait,
well, we'll
Tuesday.
discuss that
Stop
later.
it.
Think about it. Think about it, we'll discuss it. Okay, so right now we're going to do Rouche's theorem. So you have all these conditions right here. F and G holomorphic in a region G. And gamma is a positive oriented simple closed curve that contracts to 0. Here's the main part right here. Okay, so between F and G, the modulus of F of Z is greater than the modulus of G of Z for all Z on the curve. Okay, so here you have, so here's like a picture, a possible picture. So here you've got the curve like this, that's oriented positively. Okay, and on this curve, modulus of G of Z is greater than modulus F of Z is greater than modulus of G of Z. Just on the curve. Okay, that's all you need. So that's the main point right there. You know, this and F and G are holomorphic. Okay, so the conclusion is Rouche's theorem says that this number of zeros of F plus G that are enclosed by, so there's a number of zeros inside in this part here. The number of zeros in there of F plus G is equal to the number of zeros of F in there. Okay, so that is that's Rouche's theorem. And let me give you the proof of that really quickly. So I'll erase this exercise that I did here.
Nice.
Oh, you like the exercise? Okay, so Rouche's theorem is kind of useful for some of these exercises and other things. Okay, so here's the proof. Basically, what you do is use the argument principle. You just go ahead and calculate the number of zeros of F plus G. You just kind of go from there. So according to the argument principle, let's see. Kainalu. According to the argument principle, how many zeros, how can you calculate the zeros of F plus G? So think of F plus G as being our function from the argument principle. So it's actually holomorphic, right? So that means that it's meromorphic but doesn't have any poles. No poles. So according to the argument principle, the number of zeros would be, this is kind of reverse, kind of applying it reverse.
Would be 1.
1. No, it could be anything. It's not going to be a specific number. Let me ask Michael here. Let's see what Michael's opinion is.
Wait, what? Sorry.
Okay, so according to the argument principle, how can you what's one way to calculate the number of zeros? Just kind of flip things around. Okay, what does the argument principle say, first of all?
It's the sum of the zeros minus the sum of the.
Yeah, the number of zeros minus the number of poles is equal to what?
The integral of f prime over f.
Okay, so since this doesn't have any poles, that means that this right here is equal to what? Number of zeros. This equals the number of zeros minus number of poles, right? So that means it's equal to 1 over
2 pi I.
pi.
Gamma.
that's according to the argument principle.
Oh.
I see.
Is that addition or computation? That's addition.
Addition, yes. So it's basically just turned around. The argument principle would say this is equal to this. That's what the argument principle would say. We just flip it around like that. And then we do some fancy stuff here. We're going to factor out a, obviously what you want to do is factor an f out of that, right?
Mm-hmm.
So you got f times 1 plus g over f prime. And then the denominator you've got f times 1 plus g over f. Well, maybe it's not so obvious. That's the tricksy part right there. And then after that, let's see here, Anna,
Yeah.
apply the product rule to the numerator, and what do you get?
F. Oh, denominator or numerator? Doesn't matter.
To the numerator, because it's just it's a derivative of a product, so it's this times all that, right?
Derivative of the first, or
Okay.
derivative of f times g over f
Times the second one.
plus a derivative plus f times derivative of g over f. Second derivative. Second
The
one.
derivative of this would be what? The derivative that's 0, so that's
Would be g prime f minus f prime g over f squared.
Well, it's on the page
f
135.
prime
So just read it.
and f prime times g. Right? Times g over
Oh, let's see,
f prime
low.
square.
high minus high. Yeah, well, okay.
Over f prime square.
Just f squared.
No.
That's applying the product rule.
That's ingenious.
Okay, now this over this. You take that over that, what do you get?
F prime over f.
Now it's this over that.
The book just does it as 1 plus g over f. I mean g over f.
Oh, that's a good idea.
Then you don't have to worry about it.
Yeah. Oops. I should have just left it like that. Instead of having us multiply this out. There we go. So now the f's cancel, so we have so we just have that.
That's the derivative of log.
That one is. Log of 1 plus g over f.
Yeah.
Is holomorphic. And why is that? That's holomorphic because the g over f stays away from or the denominator stays away from 0. Okay, that's the reason. Or put this part right here. Okay, so that's less than 1 right here because of this. The g over f is less than 1. So that means that 1 plus g over f is greater than 0. Okay, stays away from 0. And that's and the 0 is where you, or the negative real axis is where you have The negative real axis is where you have problems with your logarithmic function. Okay.
So this is, since that's holomorphic,
Or we should say that 1 plus g over f stays away from the real part. Less than or equal to 0. Okay. So it's, in other words, it stays away from. So if here's the complex plane, it stays away from this. Okay. So this inside part here stays away from there. So that means that it's not going to. It's going to be holomorphic. Okay. And then because the derivative of this is g prime, 1 plus g prime, 1 plus g over f prime over 1 plus g over f. Okay, so g over f prime over 1 plus g over f is holomorphic as well. And that means that this integral is going to be 0. Okay, and so then the whole thing is equal to 1 over 2 pi I times the integral of f prime over f. And then what do you recognize this as?
The thing we just did.
From the argument principle, this is the number of zeros of f goes by gamma. Okay, so that's Rouche's theorem. And so the important part is you look for this. Right here. Also holomorphic. And other stuff, usually the other stuff's pretty easy to check, it's pretty standard. And then this is the conclusion right here. Okay, so let's take a look at, I did a couple exercises really quickly, probably didn't get much of a chance to sink in. So I'll do, I'll try to do something similar. Let's see here, what could we do? Okay, so let's take, I don't know what you guys choose. What power do you like? I don't know, 7?
Pi power. No.
Yeah, we did. I can't do pi. You have to be
7.
a positive or 7. We did that last time. Okay, that's okay. So we'll go Z to the 7th. Okay, and then we'll have like let's take 32Z plus 10. Dang, I don't know where this is going actually. We'll call this H of G. H of G. We'll pick that up too. Okay, so now I just kind of made that up. And we'll see what we can say about the zeros here. So the idea is that you want to break that function up into an f and a g. And the f part, you want to be able to know how many zeros it has, and then the g part, it'd be the rest of the function. Okay? So perhaps a good candidate would be so maybe we can ask a couple questions. How many zeros? inside the disk of radius 1, set it at 0? Maybe that could be the first question. Okay, so here's what the disk is right here. You want to know how many zeros inside there. And you know that on the boundary, if z equals 1, what is each of these parts going to, what's the modulus of each of these parts going to be?
1.
That's going to be 1. This one's going to be
32.
32, and that's going to be 2. Okay, so this one dominates everybody, right? So the 32z dominates everybody, so that's what you want to choose as your f of z. Okay. And the g of z, so what should g of z be in this case?
Z to the 7 plus 2.
Yeah, z to the 7 plus 2. Okay. So now, the modulus of f of z is equal to 32. So on modulus equals 1. The modulus of g of z would be the modulus of z to the 7 plus 2. And that's going to be at most 1. That's going to be at most 3, right? So that means that the modulus of f of z is greater than the modulus of g of z on equals 1, the boundary of this region. Okay. Now, how many zeros does f have inside?
What?
Yeah, has 1 0. Okay, has 1 0. So the number of zeros of h of z inside gamma this one here is equal, well, h of z is just f plus g, right? So how many is that going to be? How many zeros will it have? They'll have the same number as f, right? Which is, how many again?
What?
Yeah, just 1. Because f had just 1 0 inside, so f plus g also had just 1 0 inside.
How do you choose 30z to be an f function?
How do I choose 32?
Yeah, how do you choose 30z, 32z?
I checked if modulus of z is 1, then this has modulus 1, that has modulus 32, that has modulus 2. So this dominates the other two combined. That's why I chose that one.
Does my f of z has to always be just like normal, or can it be 2 combined?
Well, your f has to be something that you know how many zeros it has.
Like, could my f of z be equals z to the 7 plus 32z?
Yeah, it could, well, that would be problematic because how many zeros does it have inside here? It'd be kind of hard to figure that out. Okay. So, if you want to apply it this way, I think there's another way to apply it where it'd be a little bit different. Okay, but if you want to apply it this way, you want the f to be, something that you know how many zeros is. And it has to dominate the other two terms.
What if they're equal?
Then you can't apply it.
So we can only use it here.
Alright, you might be able to modify it. It depends on the example. You might be able to modify something and be able to use it. So I'm going to ask another question, and that is, so I'm going to, the same thing, I'm going to do another problem, and that would be how many zeros inside the, so same extra, same function. How many zeros inside the disk center of 0 of radius 2.
Oh wow.
So here the boundary,
So your f of z would be z to the 7th now.
is that I'm gonna take, what's that?
So your f of z is going to be z to the 7.
Okay, so z to the 7th, that's gonna be 2 to the 7th, which is,
128.
130.
that's 128? Okay, good. And then 32z, that's gonna be 64, and then the 2 is gonna be 2. Right? Okay. So, well, so you said you choose f of z to be
So there's 7 zeros.
z to the 7th? Okay. And then g of z, so you're gonna choose that. And then g of z would be the rest, right?
Yep.
So modulus of f of z would be equal to 128. Modulus of g of z, that would be less than or equal to 64 plus 2, which is 66. Okay, so we have modulus of f of z is greater than modulus of g of z on the boundary. On the boundary. Okay, and so by Rouche's theorem, like, so now f of z has how many zeros inside?
7.
Gamma. Or in this disk right here. So therefore h of z, which is f of z plus g of z, has 7 zeros.
Yay.
By Rouche's theorem.
So basically, the 2 never dominate by itself, right? The constant never dominates in the equation.
What if z is really small?
Yeah.
So you
What's that, Joshua?
You're saying the 2 never dominate. What if z was in the
In this case, yeah, in this case. Well,
0.001?
and 2
no,
dominate.
would you?
Well,
you
zero
could-
zeros.
The 2 would dominate in, let's say,
Modulus z equals to like less than 1.
maybe it would be the disk of radius 0 center. The disk of center 0 and with radius 1 over 64.
No.
And that's where the 2 would dominate, okay? Because you put a, this is gonna be like 1/2. Wait, I guess we could just say 1 over 32 would work too. We can make it a little bit bigger. We could actually make it a little bit bigger than 32, 1 over 32
What are
as
you
well.
gonna do? 1 over 17.
1 over 17.
Why?
Why not?
Maybe we could get away with 1 over 20, something like that. But the thing is, you want these two.
1 over 17 is
These two in modulus have to add up to less than that one.
Oh, okay,
Okay, those two combined together, added together.
yeah. Oh, yeah, you're right.
Okay. So you could say there's no zeros in there, for example. Okay, and then the two would dominate. So basically, if you look at both these things together, so there's 1 0 in here. And that means that there's 6 zeros in here. No. 1 0 here and 6 zeros in there. And no zeros in there. Okay, so is that
So when the distance getting larger and larger, there will be more zeros.
Yeah.
Yeah. Okay, so let's talk about the exam for a little bit here. I'll go ahead and